Here's another short set of sample problems for Math 117, Class 21. The first one brings the concept of interest rates into the picture, and it's another way of looking at the fact that if you say in a short time interval a share price is either going to get multiplied or divided by a certain factor, the effect of that is to make the price slowly drift up. So let's think about what happens as a result of the passage of time delta t. The price gets multiplied by the expected price gets multiplied by 1/2 times e to the sigma delta x, which is what happens when the price goes up, plus 1/2 plus e to the minus sigma delta x, which is what happens when the price goes down. And again, I'm going to approximate by using a Taylor series. So I have 1/2 times 1 plus sigma delta x plus sigma squared delta x squared over 2. Skipping the rest of the terms in the first Taylor series, I'll add on another 1 minus sigma delta x plus sigma squared delta x squared over 2. Throw away a bunch of other terms, and I've got 1/2 of 2 plus sigma squared delta x squared. But we're always choosing the amount by which the stock price goes up or down by using a delta x whose square is equal to delta t. So this is 1 plus sigma squared delta t over 2, which is approximately e to the sigma squared over 2 times delta t. And here's a nice interpretation of that. If the interest rate is r equals sigma squared over 2, then if I take the expectation after time delta t and discount by e to the minus r delta t, I get the original value. So there is always an interest rate which has the effect that putting my money in the bank at that interest rate has exactly the same effect on the average as letting the share prices evolve in a way where in a short interval of time they get multiplied or divided by the same factor. Now for the proof, which is the most simplified version imaginable of the binomial model for share pricing. I'm going to take the interval from 0 up to time t. I'm going to divide it up into n equal subintervals, each of which has length that I'll call delta t, t over n. And then I'm going to assume in each interval the share price gets multiplied by 2 factors. One by a factor of e to the mu delta t, no matter what, and also by a factor that equals e to the minus sigma delta x if the share price goes up, or e to the minus sigma delta x where the share price goes down, where I cunningly choose delta x squared equal to t. So let's look at the exponent for a single step. This is because the exponent for n steps is going to be the sum of changes in the exponent for a single step, and I can apply the central limit theorem to that. It's mu delta t, no matter what, that's constant random variable, plus a random variable which is as simple as can be. It is plus sigma delta x with a probability of 1/2 and minus sigma delta x with a probability of 1/2. And that random variable therefore has a variance, since the expectation is clearly 0, of 1/2 times the expectation of the square, 1/2 times sigma squared delta x squared plus another sigma squared delta x squared, or sigma squared delta x squared, but don't forget delta x squared equals delta t. Okay, what about the exponent for n steps? Well, that's the sum of n times mu delta t plus the sum of n of these random variables. But if n is large, we know all about that. It's going to be normally distributed. Its expectation is going to be the sum of the expectations. In other words, it'll be expectation 0. And the variance will just be n times the variance for an individual step, n times sigma squared delta t, but n times delta t is equal to t. So, the exponent is mu t plus sigma times w sub t. By pulling out the sigma, I've taken care of the sigma squared in the variance, but I haven't taken care of the t, so I say where w sub t has variance t. So that gives the expression for x sub t at the bottom of the problem. It does say, however, to show that it's a martingale. Fortunately, we did that last time. Or not last time, back in class 19. What we proved in class 19 was that e to the minus sigma squared over t plus sigma times wt is a martingale. And how convenient, we have mu equal to minus sigma squared over 2. So I still have to prove that mu equals minus sigma squared over 2. I'm getting a bit tired doing this calculation, so I'll do it quickly. Probability is going to be 1/2 for an upward step or for a downward step. So I will have 1/2 times e to the mu delta t times e to the sigma delta x plus e to the minus sigma delta x. Okay, that's going to be approximately, I'm doing a Taylor series, and I'm only going to keep terms up through delta t. So I've got 1 plus mu delta t times, now I've got these two terms, and the terms involving delta x are going to cancel out. So I will get 2 plus 2 times sigma squared delta x squared over 2. And you say, what are you doing keeping terms in delta x squared? I have to do that because delta x squared is equal to delta t. So what have I got? I've got 1 plus mu delta t times 1 plus sigma squared over 2 delta t, or 1 plus mu plus sigma squared over 2 delta t. And I want this term to be 0 for a martingale. So mu has to be minus sigma squared over 2. And in that case, my e to the mu t turns into e to the minus sigma squared over t, sigma squared over, I wrote this wrong, sigma squared over 2 times t, and my proof is done.